So let's start off with a motivation for the second variation. Now we've seen in the previous course when we covered the first variation, we looked at a hanging rope. So I've got a rope here hanging over a couple of pulleys. And we said that the rope hangs in such a manner that it minimises a particular quantity. And the quantity that it minimises is the gravitational potential energy. So we've written this down as the gravitational potential energy at the surface of the Earth. So we'll just call it energy potential equals mass times gravity times height, just to keep it simple. Now we said that if we were to take our finger at one point of the rope and pull it down to a new point, then we're going to have a positional change. So we're going to have the original function f, which is this function here, which is in the equilibrium position, and we're going to have a positional change of that function. Now also when we move it from one point to another, we're also going to have a gradient change, because when we move the point from the rope from this point to this point, we're going to have the gradient changing like this at one side and like that at another side. And this is going to be the first variation. So this is the f derivative, or the first derivative of our function. And this is our gradient change. And we've seen that we derived the Euler-Lagrange equation by looking at first the positional change, which was given by this part of the Euler-Lagrange, partial f by partial y. And then we looked at the gradient change, which was given by the second part, which is the partial f by partial y derivative, which is the gradient change here. But the gradient changes in a different manner from the left to the right. So to incorporate the gradient change from one side and another side, we differentiate it with respect to dx. So that's how we get our d by our dx. Now what we said is if we were to set both of these changes equaling to 0, then we would say we would be back in the original equilibrium position. That is, the position wouldn't have changed and the gradient wouldn't have changed, and we would be sitting with the original position of our rope. Now this equation here is called the Euler-Lagrange equation, and we said that if we found a function y of x such that this equation was satisfied, this differential equation was satisfied, then we would have found a function y of x which in this instance would have minimised a particular quantity, and the quantity it would have minimised was the gravitational potential energy, and that would ensure that the rope was sitting in an equilibrium position. So we would have worked out the equation of a hanging rope, and when we did that in the last course, we've seen that we come up with an equation which we called the catenary. But that isn't the end of the story. Not only can we look at the gradient change, which is a rate of change of position, and this is our first variation, we can also look at a curvature change, which is the rate of change of the gradient. Now we could also look at higher order changes, so we could look at the rate of change of the curvature, and so on and so forth. So we could look at the first variation, the second variation, and we could have a third, a fourth, a fifth, sixth, seventh, eighth, so on and so forth variations. It means that for each of these different variations, in effect we would come up with a different equation here. So in effect you could say we could come up with a second variational equivalent of the Euler-Lagrange equation. So in this course we're going to be looking at the second variation, or if you like to think about it in terms of a physical example, we would be looking at the curvature change of this hanging rope. So why bother with this second variation and higher order variations? Well, let's have a look at that in the next slide. So in order to understand why we're interested in the second variation in the calculus of variations, let's look at an analogous example from simple calculus. Let's say we've got a function here, f of x. We know that if f derivative of x is equal to 0, say at this point here, then it means our function in this instance here would have a local minimum. But we could also have f derivative of x equaling 0, and we could have a local maximum. We could also have f derivative of x equaling 0, in which case we could have an point of inflection. So the inflection could run this way, or it could run this way. So having f derivative of x equaling 0 is not enough to tell us whether we have a local minimum, maximum, or inflection. It only tells us that we have one of these three. We need to have a test in order to nail it, that is, in order to decide whether we actually have a local minimum, maximum, or point of inflection. So what we say is that if f derivative of x is equal to 0, then this is a necessary test for a local extremum. So by extremum we mean one of these three. So f derivative of x equaling 0 is a necessary test for telling us whether we've got a local minimum or a maximum or a point of inflection. But it's not a sufficient condition to tell us which one that we have. Now, from basic calculus, we can look at the second derivative. If the second derivative is greater than 0, then we're going to have a local minimum. Also, if the second derivative is less than 0, we're going to have a local maximum. Now, if the second derivative is equal to 0, we're no longer able to tell whether we have a local minimum, maximum, or point of inflection, and we would have to look at a third derivative, and so on and so forth. So what we say in mathematical speak is that if f derivative of x is equal to 0 and the second derivative is greater than 0, then we have a necessary and a sufficient condition for a local minimum. If f derivative of x is equal to 0 and f double derivative of x is less than 0, then we have a necessary and a sufficient condition for a local maximum. You'll also hear these terms necessary and sufficient used an awful lot by politicians trying to impress. So the same occurs whenever we're looking at calculus of variations. So when the position and gradient change is set to 0, that is, the Euler-Lagrange equation is equal to 0, then we have an local extremum. But we don't know whether that extremum is in fact a local minimum, a local maximum, or a point of inflection. So we need to have another test. That is, we need to look at the second variation in the same way that we looked at the second derivative for the simple example of basic calculus. So if this second variation was greater than 0, that is, it's positive, then we would be able to say that our extremum was a local minimum. If the second variation was less than 0, that is negative, then we would be able to say that our extremum would be a local maximum. So we want to look at higher order variations in order to prove that we have a local maximum or a local minimum. Now we also learn more about our functions and our calculus of variations by looking at higher order variations, but we'll get into those through the rest of the course. But that gives us a motivation as to why we want to look at higher order variations. So let's work out a roadmap of where we're going over the next few videos. We want to work out this equation here, f double derivative. So this is going to be the total derivative of the second variation. And having found this, we're going to have to work out whether it's a positive value, which would mean a local minimum, or a negative value, which would mean a local maximum. So as we've said, we're going to find the f double derivative, so that's the second order total derivative of our functional, and we're going to have to work out whether it's positive or negative. Now this equation here is difficult to work with. So what we do is we can introduce another equation which we can call the Jacobi accessory equation, or we'll just name it JAE. And this Jacobi accessory equation, we can use this in order to simplify the first equation. And when we've simplified the first equation, it makes it easier to work out whether it's actually positive or negative. So don't worry too much about this here. We'll see exactly where this Jacobi accessory equation comes from, and we'll work through how we are able to simplify the second order total derivative in order to work out whether we've got a positive, which would give us a local minimum, or a negative, which would give us a local maximum. So let's crack on, and we'll do this over the next few videos.